Okay, so today, we're in this a very good session called supervised image classification with convolution neural nets. So this is our lecture 13. So again, just let's recap what we covered last week. We have covered the basic neural network models, and then we give this 6 components for the classic neural network models. But actually beyond that. So far, the deep neural networks can handle so many different kinds of data types, and they can do regression and classification. And what we covered is just the basic multilinear linear perceptron. And today we're going to move beyond that, cover convolution neural nets. And the scoring function, when we use for the classifications, we covered cross entropy loss. And then we covered a little bit about back probe, the forward step and the backward step. So the most important there is you need to think about the components of this convolution neural nets is block by block and layer by layer. And then every one of those blocks are differentiable. So you can do forward and input some input vector and then generate output vector. For every block, you in the feed forward step in the back probes, forward step, you actually memorize all of the middle output from each block. You need to calculate the gradient. And in the backward step, you use those output and also the gradient generated by that specific block, and also the gradient passed from those other blocks that follow you, and to generate the gradient that you're going to send to the blocks that before you. So that's really the essence of back probe. And then we did not get time to talk about metrics to evaluate classification, which I'm going to cover a little bit today. Okay, so before I jump into convolution neural nets, I again want to review the histories. So because I think always I found history tells you a lot of reason behind why something is now. So we actually talk about this in the first lesson of the class. So you can think about AI starts from 1950s, and the first machine learning solution for that AI problems is the Samuel's checker player. And then in the 1950s and to the end of 1960s, in fact, there are a lot of work on neural networks. And then in 1970s, there's neural networks got cooled down, and then the rule-based type of decision tree-based or graph-based, like net-based method kind of dominate. Then in 1990s, convolution neural nets, which we're going to cover today, and also recurrent neural nets, which we are going to cover next week, were invented. They are, in fact, the workhorses for the current deep learning. And so they were invented actually in 1990s. And then in the 2000s, and what actually got popular, it's not neural networks. They're support vector machines, graphical models, matrix factorization, which we're going to cover after the deep learning session. So why in the beginning of the 2000s neural networks got almost like abandoned? It were really the winter, because around that time, researchers favor the convex type of solutions, but neural networks are not convex. And so we have to talk about the convex. Like when you have convex loss function formulations, it's really easy to guarantee that's a global good solution. But when you don't have this convex properties, you really don't know, am I in the good solution or in a bad solution? And the other thing is neural networks are just so flexible. One, it's so flexible, but you don't have enough guidance. And then we actually show that exactly through this bias and variance trade-off, right? So in the bias and variance trade-off, like on homework 2, your model, like in that polynomial case, it's just so flexible with the high D. You don't have enough training data. It's very easily, you're going to overfit the training data. And then the neural networks just there's so many tricks like the layers, the hidden number of hidden units, and then different kind of topologies. It's just very hard to play when you don't have enough guiding data set. And also back then, you don't have a lot of labeled data, and people, majority of the problem are not digital yet. And now, 2012, start from this ImageNet competition. First is almost everything goes in digital. So your historical data, people's daily life tracking data, the social network got so popular, smartphones, smart devices got very popular. Your data starts to get recorded in a very easier manner like the cloud now, so in the digital form. And this is extremely important. Once in the digital form, and then people start to hire labelers to label them, to give this kind of guidance, right? When we have enough training data, how do you tune the bias variance trade-off? I mean, we actually covered that. One of the most important, really, really important, is to have more training data. It's a very effective strategy to do variance and bias control. So with this as the background, then together with the NVIDIA, like this GPU support, and that can make this humongously flexible models to train fast and also predict fast. Then we solve the bias variance issue. At least we have training data to control that. And then we also using digital, we also have this computer architecture to support the scalability issue of this type of model that we cannot solve in before the 2000s. So that's the reason why, I mean, it's just all the three things together click and create this, people call that miracle or deep learning breakthroughs. But in fact, it's really technology involves multiple factors. And then it really needs them to be all ready, and then together they create something amazing. So, and then that's from 2012, and then this performance just got improved in the ImageNet classification task, the object recognition task. So the in 2017, and this is almost it's like human performance. And all of this are actually based upon the convolutional neural network architecture, which we're going to cover today. All right, so now let's see what we're going to cover today. So we will focus on 2D imaging data type, and we will focus on convolutional neural network as a block, in fact. And we will cover a little bit about how do you measure classification task. Okay, so first, what we have covered so far, it's about tabular data. So tabular data, you can just think about as a matrix. We're very, very familiar with it. And actually the pandas data frame, you normally read into, if you use whatever packages, I mean, you normally read them into a matrix form. So, and this is very classic. Everything we covered can work on that type. But when you have this kind of imaging data, so this is the 2D grid type. So what do we mean grid or lattice? So which means you can think about them as this regular spaced geometrical points. So it's very regular, and in this case, it's just two-dimensional. And then there's a relationship among the points that are neighborhood to each other on this lattice. So let me write down, maybe just again using extremely simple examples. So assuming we have, let me just do maybe 3 times 3. So this is a 3 times 3 image. If I just want to assume an image like an X, so I would just, so this is an X shape image, and it's in fact represented in the computer as, so let's just use binary, like black and white. So this is like represented as 1 0 1 0 1 0 1 0, 1, right? So this is my image of X. So what makes an X? If you think about it, what makes an X? It's really this left cross and right cross, right? That's the thing actually makes an X. But if I don't keep this two-dimensional representation, I just represent it as like 1, 0, 1, 0, 1, 0. Oh yeah, I actually can write it like that because I can just write as old x1 to xp, that's our old representation, right? x1, x2, in this case is x9. So this is like 1, 0, 1. Okay, I think I can 0, 1, 0, 1, 0, 1. So onto x9. And then I can label this as the class X. So my Y is a X, class X. Maybe it's X or not X. I can just represent it as yes and no. Yes and no. So if you have multiple different X, because some people write X like this, some people write X like this, some people even have more crazy handwriting, you can always represent it into in tabular form. But why don't we do that? The reason is, so I'm going to talk about that later, because there's some kind of spatial regularities in imaging. So for example, let's just use this most classic face as example. I'm going to write in this this gentleman's face, I'm sorry, but I just want to make a point. So when we see the human face, there's actually this pattern, right? Very clear pattern. Your eyes, your nose, all has that kind of spatial relationships, and that makes it a face. So we want to design detectors to be able to carry that type of relationship, and spatial relationship among the features is important. So that makes this different from the generic tabular data, because there are relationship among, in this case, so this is x1, this is x2, x3, x4, x5, x6, x7, x8, x9. There are relationships like x5 and x6 are spatially neighbors, and x2 and x7 are not spatially neighbors. So now I'm going to first show you a few like a code around notebooks on COVID-19 CT scan. But before I'm showing the code, I want to review something. Again, model selection and model assessment. So you already code this in your homework too, but I still want to just kind of emphasize because this is extremely important workflows. So we always have a stage model selection is to estimate to tune the hyperparameters or to select among different model class. So when we saying report your prediction error, that's not about model selection readout. That's about the readout what you already chose a model, and then you use that hyperparameter or that chose model class to retrain on both the train and validation data, all of the possible those data, not about the test. And then that using that model, applied it on this new data. We normally call this testing fold. And this testing should not be touched by every stage, right? Like not about testing. It shouldn't be touched by training, it shouldn't be touched by validation. So this is just very, very important. And then there are different ways to do this model selection and model assessment. And what you actually have done in the homework, you cover the two kinds. So the first kind is just you split the data into train validation test, and you perform using train and validation to do model selection, and use train and validation together to train the model, the final model, and then use the test to do assessment. But in fact, there are a lot of variations of this. So for example, variation is, so when you don't have enough training data, you actually can do something called bootstrapping. Bootstrapping means, all right, so the train validation, I just randomly split once, right? But I can randomly split twice. I mean, similar split ratio, and you're going to get like maybe B different bootstrap train validation, and those give you a very good uncertainty estimation of validation error compared to if you have only one split. That's called a bootstrapped version of train validation model selection procedure. And the other way is just what we let you implement. It's okay, we don't do this random split. We actually do cross validation to make use of every sample in that train fold, and to both as training and both as validation. And so you already implement that. It just to the bootstrap is a good practice actually many people use. And the other thing we did not cover is when picking the hyperparameter tuning, you can also use some kind of analytical measure. For example, AIC, BIC, MDL, these are more, it's really a calculation. You can actually have an analytical form of what is the best based on this kind of approximated analytical form to pick the best hyperparameters. So if you're interested, actually feel free to check out the Element of Statistics book about AIC, BIC, and MDL. Okay, so this is what we covered, train validation test and cross-validation. And so this threefold, it's actually used in a lot of deep learning pipelines because our reference data is just huge. And if your data is not too huge, I highly recommend you to do K-cross validation. Of course, this is it's kind of relatively expensive. Yeah, more expensive, more costly. All right, so enough of this. Then the last piece is about how do you measure classification. So assuming we just have two classes, a yes or no, or true or false. So what you're going to get, it's like, let me actually write it here. So for every sample, you're going to predict there's a y1 hat, there's a true y1, and then there's y2 hat, and then there's a y2 from your label data, and then on 2, so let's just assume that there are m of this. There's m like in my testing data, so versus the ym, the truth. So the most important when measure the classification is to generate this matrix called confusion matrix. So it's confusion matrix, and to get the confusion matrix, this is a binary case, right? So it just it's the, because they're only true and false. So you really just fill in this item by counting. So because here you actually, if my true y1 is plus, it's my let me see how to write this easier. So you can actually write down, right? So y hat and y, so you just treat it as two list. So y hat, y. So if y hat is positive and y is also positive, your true positive will plus 1. All right, so that's a true positive number. And if this is the case, like true and false, so I'm predicting as true, but my true label is, let me write as a plus. Oh, sorry. So just make it a little easier. So they're in fact, they're all in like 4 cases, right? So I'm predicting as a positive, my true label is negative. So this means what? This is a false negative. Oh, I see. Actually, my table, it's pretty clear. Yeah, so I can just write as, okay. So the actual is, again, so actual is the true y, and predicted is the y predicted. And then you really just fill in this occurrence table, and then by counting in your array, and then you just you can get true positive, false positive, true negative, false negative, and true negative. And what you really like is this diagonal term to be very, very large, right? Everything in the diagonal is larger, and then everything off diagonal is 0, right? So this is only for the binary case, and we're going to show you a like all those different kind of unbinary case. I mean, when you have multiple classes, you're just generating the same kind of matrix just by having more columns and more rows, and this is a symmetric matrix. So then, using this confusion matrix, you can generate all different kinds of numbers. Like in this case, the most classic is the accuracy. So the number of correct prediction over the full size of the testing data. Precision is the number of true positive over your predicted positive. And then recall is the true positive over the actual positive. So there's also F1 score, there's also mean average precision. There are actually a lot of other metrics. So the most used normally is the accuracy. All right, so now I'm going to actually start to talk about deep learning frameworks, because it's just it's such a great now. It's really a movement now. It pushes the AI to get really popular and seems to get more real. So there are so many deep learning frameworks and the libraries. So the most stand out, I think now, is the TensorFlow and PyTorch. And so in the homework 3, we give you two choices. You can either pick to use Keras, or you can pick to use fastAI. So Keras, you can think about it's an easier to use interface on top of the TensorFlow, and the fastAI it's easier to use library interface on top of the PyTorch. So there are more like notebooks in. So Keras is like more. It just fastAI. It's younger, so let's use that term. So I really like fastAI, and it's also very funny. Their word is making neural nets uncool again. So this time I initially want to just go with PyTorch and fastAI, but then I realized there are some students actually prefer TensorFlow more. So that's why we give you two choices. You can just pick either to use fastAI or Keras. If you like, you can also do two. I mean, it's actually really great if you learn two. All right. So the data we're going to use is the fashion MNIST data. It's almost the data besides the MNIST hand digit recognition data. We will hold the homework more like a Kaggle competition type. So the top, I think I rate maybe top 10 students in the leaderboard will get a little bit extra credits. So just make it a little fun, and feel free to play with the different kinds of models. So if you want to build a 3-layer MLP, just like we reviewed last Thursday, it's actually very, very simple. You just use the torch and module, and then you, in fact, just do linear. It's just one layer, and then you add another linear layer, add another linear layer. You got 3 layers, and then in the end, you get add a sigmoid, and then this gives you a binary classifier. So, and then the forward step, I mean, it's also super simple. You kind of memorized H1, H2, those middle generated samples, generated variables. So we actually showed you last time. So this is X and H1, H2. They are all vectors, in fact. And then the output Y hat is the class output. You really just write out like this forward from block to block. And that's your 3-layer MLP model. So it's even the raw library is in fact very easy to write. All right, so now I will switch my computer to show you some code. And one code is actually from a Kaggle competition on that CT scan COVID data. The other is I wrote using the fastAI. Okay, so yeah, so this page is the CareSpace. If you are interested in finishing the homework 3, and this is the page you actually should check out. I mean, what is how to write a convolution 2D, what are the parameters, right? So you can actually tell in this 2D Conv 2D, so you're going to get more familiar and after the class. So the first is the filter size, the second is the kernel size, and then you have stride and padding. So we're going to talk about in the second module. So let me just show you this data. So this data is from it's very recent data. It's from Kaggle competition, and then it's from Brazil. I think it's about like 1,200 CT scans for the COVID-19 infected patients, and also almost an equal number of non-infected CT scans. So in total, this has about like 2,500 CT scan imaging. Like fastAI make it very easy to load the data. So I can show you actually some like my data, how I organize it. So this is in my drive. I organized this this is my SARS-CoV-2 CT scan data. So I just provide this in fact two folders. One's called COVID, the other is non-COVID. And then they just generate a model. And you're going to see how I generate this model. And inside each folder, COVID and non-COVID, this is actually organized by the Kaggle data already very nicely. And then these are the imagings, and it's also very nicely indexed. So this is the SARS-CoV. This is one way to organize your data. So you don't have a train validation split. You're going to use code to do the train validation split. So there's another way, is what I actually showed you before. So what I show you actually my cooking image classification before, I actually did the split by myself. So you can just organize your data into the train fold. Inside the train fold, you do the 3 classes. That 3 class, sweet, non-sweet, and coffee, is your class label. And inside the sweet, I have my images, and all the images I labeled as sweet. And then coffee, that I labeled as coffee. All right. So very similar, and you organize your validation. You can organize your validation folder the similar, and then you can also have the test. But the fastAI actually doesn't use the test fold. You do it, and I'm going to show you now. So these are 2 different ways to organize your data to load into the fastAI. And also the fashion amnesty data, in fact, the fashion amnesty data, what we give to you, in fact, we already flattened it into a CSV form. So we already give you in the CARES sample code, we read it into a data frame. And then fastAI can also load from a data frame if you already put it into a data frame. So just to clarify, this one code we give to you can work in both CARES and fastAI. All right, so now let's come back to our SARS-CoV-2 scan. And I already shared you this code in our slides. You actually can just copy it in your Colab, run it by yourself. But you have to download that data first, organize it just like what I did. All right. So I will not run it because it takes a little while to run. So this kind of code tell you how to load from your drive, from the Colab. And then it's very easy. We just use this image data bunch from folder function and directly read that folder I just show you. I think there are only two folders, non-COVID and COVID. So this library knows there are only two classes you want to predict your classes towards. All right, so you load it, and then you can give this validation dot proportion. I mean, in this case, I just give 0.2, 0.2, 20% as validation. Very simple. And then the library automatically do the split. Yeah, so that's why I see, but if you use CareSpace, you have to use the train test split function you had before. If you use fastAI, in fact, this is even more higher level than the CareSpace. You can see just from data loading function. And then you can just draw, I mean, like this data. So it's very nice. They provide you this kind of normalization function, normalize just into, because, you know, sometimes the images are not captured the same size, right? For example, my phone images, some are from my phone, some are from maybe my other family member's phone. So they're really, some are even downloaded. So they're not the same size. I mean, you need to give same size data, and then the fastAI has really good normalization function there, and then you can just show it, and this actually shows a batch of the data you just load, and then this has non-COVID and COVID, and then you can just talk about that. You just do metric, and then you create CNN. This is actually extremely high level. So this just one line of code actually create the CNN models using this from the ResNet34. So I'm going to talk to you what is ResNet34 in the second module. So this is a very popular existing imaging classification model trained on imaging networks. There are 34 layers. You used it's a convolution neural network architecture, heavily using something called residue layers. So, and then you just create this by one line of code. Then you can print out and to look. I mean, so if you look at this ResNet34, so I think this is the downward. It has the sequential up wrapper. In the CareSpace version, you actually need to have a sequential wrapper, and then you have convolution 2D, batch norm, ReLU, max pooling, and inside you have another sequential, and then it's a very complex 34-layer convolution neural networks. All right, so I did not train anything actually. I just loaded, and then I directly classified my COVID-19 data. So this is the confusion matrix I just told you, like this is the one, right? This matrix summarizes everything about your prediction versus the true labels. And you can actually tell this predict very badly. This just predict everything as non-COVID. All right. So, oh, actually it's it predicted everything as non-COVID. And I just get off the shelf trained on ImageNet, and it really doesn't work on this. Okay, so, and then I can also use this function called plot top losses, and then just show you everything is predicted. So prediction, first label is prediction, second label is actual, and then there's a loss. There's also the probability of that prediction. Yeah, it was actually predicted very badly. You can actually tell. I mean, it's just, you can tell, I mean, this ResNet34 really doesn't know how to predict on this new data. Okay, so now I can just do the simple fine tuning. I'm just training like, I just train once, train one step, and on my current, and then save that data. And then it's already actually better than the that off-the-shelf result. And then I can show you this is a retrained model. I trained actually only one step. And then this actually it's not bad at all. So this actually give me like the majority, like we actually told you, right? Confusion matrix, the diagonal term, the higher the better, and the off diagonal term, the smaller the better. So they're a little bit off diagonal. Is there 60 here, 22 there, and they're actually not much even model selection, right? I didn't tune anything, the hyperparameter. I just fine tune it using my training data, and it's got good validation performance. All right, so now I try to do model selection. So here, my model selection is to tune that learning rate. So this is a function, and then they're just doing fine tuning. Yeah. So, and then you got the best optimal learning rate, and you can use this. This is really in our validation curve, right? So learning rate is the hyperparameter, and then the loss is my metric. I got this kind of valley shape, and I'm picking the best learning rate, and then I'm refeeding using that best learning rate, and then retrain the model, and then I can just show the loss, and this gave me a little bit better than that no cross validation, no model selected learning rate. This, if you pick a better learning rate, it gives you a little bit better performance. This, yeah, at least the 16 wrong predictions before in this lower corner now got like improved into 20, and it still can be improved. So now I show you the loss. I mean, this predicted versus the actual. Honestly, I cannot tell much because I'm not a pathologist. I really don't know anything why this got predicted wrong, even though I can see this. But I think this kind of visualization function will be really helpful to the experts, right? So there are many people saying this deep learning based imaging will replace pathologists or replace those health profession person. Honestly, I think that's just overclaiming. I feel like in the end, we need to think about this type of AI tools are good tools, and the tool itself is to help, and it's I'm very sure it will be part of the workflow for those health professionals using the imaging, but I actually don't believe it's going to replace them. Yeah, that's just my summary. All right, so and then I actually download this from the internet. Has nothing related to this specific Brazil CT scan data. Again, I have no idea what is this. I just downloaded from the web, and then I save locally. Yeah, this testing data. Yeah, so all right, so this is another notebook, in fact, from the Kaggle competition, exactly hold on this data, this Brazil CT scan data. So again, I'm not going to run it because it takes a little while to run that. So the thing I want to show you is, so this uses a different model. So I used the ResNet 34, and this uses a much different model called DenseNet 121. So this type of model normally has a number, and this number you can think about, this means the number of layers. So this, so let's see. So you can actually see it also uses a different way to create a model. So this is CareSpace. So it also adds something. It also has a pre-processing on the imagings. The image I use in my notebooks, I did not do anything like a data augmentation, and data augmentation is actually extremely important in this imaging-based classification. So feel free to check it out if you want to learn it, and if you want to win in our Kaggle style homework 3. And let me show you the results from this person's notebook. Okay, so let's see this confusion matrix. The confusion matrix, I think it's a little better than mine. Yeah, it's a little bit better than the one I showed you. I actually ran it. So they have this like 15, and this is similar. So, and so this is everything almost everything you need to know for the homework 3, and this will prepare you very well for the homework 3. So there's really good libraries. You can just click the fastAI with the DICOM reading and all this pre-processing, and it's almost like no effortless here. So all those great library really makes the deep learning based imaging prediction task seems to be super feasible now. I hope what we learned, if you are a biomedical imaging student, I think this will be very helpful if you're doing research. All right.